Have you ever wondered how your music app can just, instantly add a new song right into the middle of a massive playlist? Well, the secret is this surprisingly simple but really powerful data structure called the linked list. Honestly, it's the hidden engine behind so many things you use every single day. So, let's dive in and see how it all works.
So, to really get why we even need linked lists in the first place, let's start with a problem that you've probably run into without even knowing it.
Okay, picture this. You've got this huge playlist, right? Hundreds of songs, all perfectly ordered. You find this amazing new track and you want to slide it in right at, say, position number 50. But for some reason, your computer just seems to hang for a second. Why does it take so long to do something so simple? Well, the answer is all about how that playlist is stored.
See, most of the time, a simple list is stored in what's called an array. You can think of it as a big, continuous block of memory. So to add your new song at position 50, the computer has to literally move song 50 to position 51, then move song 51 to 52, and so on. It has to shuffle every single song that comes after it. It's this massive, slow, inefficient process. In computer science, we call this an O(n) operation, which is just a fancy way of saying the time it takes gets bigger and bigger the more songs you have. More songs, more weight.
This is where the magic of a linked list comes in. Instead of shuffling everything, a linked list just does two tiny things. It tells song 49, hey, from now on, you point to this new song. Then it tells the new song, okay, now you point to the song that used to be at position 50. And that's it. All we do is update two little pointers. It's unbelievably fast. We call it an O(1) operation, which means it takes the exact same tiny amount of time whether your playlist has 10 songs or 10,000.
So that super clever solution we just talked about, that is a linked list. It's not a block of data, it's a chain. Let's break down exactly how that chain is built.
The fundamental building block of this entire chain is something called a node. And a node is incredibly simple, really. It just holds two things. First, the actual data, your song title or whatever, and second, a pointer, which is basically just the address of the next node in the chain. That's all it is, data and a signpost to the next piece of data.
Building one is actually pretty logical. You start with a head node, that's your entry point. Then you create another node and you just link the head's pointer to it. You just keep doing that, creating this chain link by link. And how do you know when you've hit the end? Well, the very last node's pointer doesn't point to another node. It points to null, which is like the universal computer sign for stop. The chain ends here.
Okay, so now that we've got the basic concept down, let's look at a few powerful variations on this idea, because as it turns out, not all chains are built the same way.
First up, we have the one we've pretty much been talking about this whole time, the singly linked list. The easiest way to think about this is like a one-way street. The pointers only go forward, so you can easily travel from the beginning to the end, but there's no way to turn around and go back.
But what if you need to go backwards? Well, that's where the doubly linked list comes in. With this one, each node has two pointers, one that points to the next node, just like before, but also another one that points to the previous node. This creates a two-way street, which lets you move freely in either direction, forward or backward.
And finally, we've got the circular linked list. This one does something really clever. Instead of that last node pointing to null and stopping, it points all the way back to the very first node, the head. This creates a continuous, endless loop. There's no real beginning or end, just a constant cycle.
So where does all this abstract stuff actually matter? Just about everywhere. The next and previous buttons in your music app? That's a doubly linked list. The back button in your web browser? Yep, doubly linked list. Your computer's operating system uses circular lists to cycle through all the programs that are running, giving each one a little slice of processing time. And that amazing undo-redo feature you can't live without? You guessed it, that's a doubly linked list, keeping track of all your changes.
Now, linked lists are super powerful, but they're not a silver bullet. They're not perfect for every single situation. And like any tool, they come with a very specific set of pros and cons. Let's look at those trade-offs.
So on the plus side, linked lists are dynamic. They can grow and shrink really easily. And as we saw, adding and removing items is incredibly fast. But here's the catch. You can't just jump straight to the 100th song in your playlist. You have to start at the beginning and follow the chain, link by link, through the first 99 nodes to get there. That's slow. They also use a little bit more memory because of all those pointers, and they can be less cache-friendly, meaning the computer's processor can't access the data quite as efficiently as it can with a solid block like an array.
Okay, and here's where it gets even cooler. Beyond just being useful on their own,
Linked lists are also the foundation for other critical data structures. They are, quite literally, the building blocks for how we manage all kinds of ordered data.
So let's talk about the stack. The best analogy is a stack of plates. When you add a new plate, where do you put it? On top. And when you take a plate off, you also take it from the top. The last plate you put on is always the first one you take off. This is the LIFO principle. Last in, first out. And this is exactly why linked list is the perfect tool for building a stack. Adding or removing from the top of the stack is the exact same thing as adding or removing from the head of a linked list. And we already know that that is an extremely fast O of 1 operation. It's a perfect match.
Now let's switch gears to the queue. Think of a line at a checkout counter. The first person who gets in that line is the first person who gets to check out and leave. This is the first in, first out principle, or FIFO for short.
See, queues need fast additions at the back of the line and fast removals from the front of the line. A linked list handles this perfectly, with just quick pointer changes at both the head and the tail of the list. If you tried to do this with an array, you'd have to slowly shift all the elements over every single time someone left the front of the line. What a nightmare!
So we've covered what a linked list is, its different flavors, and what it's good for. And this all really boils down to one crucial question that every developer has to ask themselves.
In other words, when should you pick a linked list, this flexible, dynamic chain of nodes, over a simple array, which is that rigid, solid block of data?
Here's the bottom line. You reach for a linked list when your data is dynamic, when it's constantly changing, with items being added or removed all the time, especially from the middle. You choose an array when your data is pretty stable, and your main priority is being able to quickly look up items by their position. At the end of the day, it's all about picking the right tool for the right job.
And that's our deep dive into linked lists. Now that you know how they work, I bet you'll start seeing their influence everywhere. So think about it. What other parts of your digital life are secretly being powered by these simple, clever little chains of data? Thanks for joining me.